Thank you very much for giving me voice. Today, I will talk about gasification and addition of phosphorocatalytical uh, or mechanocatalytics to the municipal waste to enhance. Here is as an energy oxygen carrier. However, it has also photocatalytic and mechanocatalytic properties. Is copper iron oxide is a photocatalyst and ligand, which is both photocatalytical and mechanocatalytical, so able to form due to friction with catalyst or by light to split to produce such potential that can split the surrounding compounds. Uh, their work is based on an article of Professor Xuantang Xu from Guangzhou University in China and Key Laboratory of New and Renewable Research. The work is published in this year Energy Conversion and Management in this August and is entitled The Hydrogen Production from Municipal Solid Waste via Chemical Looping Gasification using copper iron tetraoxide spinel as oxygen carrier and aspen plus malic. With that, what provides the gasification is one of methods of conversion of municipal solid waste into some gases via quality syngas processing can be produced of biofuel, can be tar, can be liquid lower carbohydrates like octane, kerosene, and this gasification is thermal decomposition with usually with addition of oxygen or of with oxygenation, and here we get the catalyst spinal copper iron oxygen to provide lattice oxygen. This model was validated using experimental results and then improved view and modeling by Aspen program. The case is that the why they make landfilling and growing municipal solid waste with growing population demand improvement of utilization of waste, of transferring them. And growing population is too high, number is too high to be suitable then for fulfilling the demands using mining earth crust sources. And due to this fact, both carbon, energetic, and material needs to be used from the renewable and sustainable methods or from waste already mined sources, which should be should be enough to fulfill our demands. Of course, if the population will not grow too much, because it will grow above 30 billions, it will nothing happen because it's the limit of this F that above 13 billions it will be too much, and 12 billions is the limit, higher limits, and we need to something make. And so it's done, but it's not the case. Here we have some option to make enable, and thus is the classification is employs a fuel reactor and air reactor to restore lattice oxygen using long valent oxide. The oxidation circulation oxygen oxygen uh, mm, oxygen carrier is using for both lowering the temperature, so lower needed energy, more efficient heat transfer from air reactor to fuel reactor, so reducing cost, reducing material potential, and the case in this is also catalyst. This is the perfect case. This using choice of metal oxide due to exceptional magnetic and thermal characteristics and catalysts. Carbon iron oxide shows strong reactivity, enhancing fuel conversion rates, and maintains stability of its cycles with excellent sintering resistance. Additionally, the lattice oxygen is most susceptible in partial oxidation reactions, resulting in higher classification efficiency of 89 even 82%. So here we get the hydrogen oxide, and in this temperature is good for using pressure swing adsorption, which is nowadays the basic method for separation of hydrogen, for for purification of hydrogen for multiple gases phase, and this is the basic material beside membrane. But membrane are still very low efficient, and pressure swing adsorption is still one of the more conventional. And see the other advantage of gasification that we already have much reactor because it was already made by fuel technology. So we just change the feed from fossil fuel into some waste that needs to be utilized and transferred to other. So has using this process, this using uh, dual fluidized bed gasifier is as follows. Municipal waste goes with oxidative catalyst, oxidative carrier here, spinel, iron, tetra, copper, iron tetraoxide to fuel reactor. In this fuel reactor is also getting cycle which put the air to the air reactor and circulating the air, and then the produced gaseous phase is then filtered to reactor and so the waste gas waste gas gasification water gas shift reactor. So by stripping is giving a scrubber, and the rest is going to steam generated that cooled out the fuel reactors, and then after scrubber the gases phase is going to pressure swing adsorption, which purifies hydrogen and separated from other gases are clean. The other case that air reactor is also fueling the bottom products which are filtered, and then during filtration is nitrogen we recovered, and the bottom part can be used for production of polymers of other substrates. So we can use for biochar as for biofertilizer. So this some application. This is higher maybe frequency than using pyrolysis, but this water phase shift and purification is very important because gasification always also produce more toxic gases that needs to be catched before releasing. So this purification is very important and more needs to be more sensitive and more precise than in case of pyrolysis, which is producing less. So oxygen helps in better waste utilization, but in other hand, we need to prevent to the undesired things and still is produce some carbon dioxide, which is unlikely. So we need to combine after this these gases with some maybe plants, maybe some capture of carbon dioxide to some place. So this is the case to not produce in it to not produce too much um, greenhouse gases. As a result, we get of municipal waste the 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 production and approximate so the volatile matter was 77%, while ashes was 14%, and carbon oxide is the content of sub-municipal waste was hydrogen was just 7%. What was the case? The reoxidizing, the structure during case goes to from tetrahedral to octahedral position and carry which catching the carbon substances, and in fact in this case the released gases phase was 50% in experimental fraction, which was higher than aspen production for 4%. So, but releasing much monoxide, carbon monoxide, more than model shown. So the only carbon dioxide also was in modeling higher than experimental. Only the lower was the higher that well, there was uh, hydrogen experimental, and methane was also far above model model experimentation. So the model was a very uh, pessimistic way. So in result, working that works better than supposed. So this is the information that Papa has some specific uh, apply specific conditions which changes the structure. This structure help some attributes not mentioned in this model, and the scientists will for sure cooperate why more in next work to explain this case. The model underlying primary assumption. Sulfur reaction yields only hydrogen sulfide, which can be some case. Nitrogen oxide yields only nitrogen ammonia. Tar and hydrocarbon, where except methane are not considered. And we know that carbon tar was even 7-20%, so quite high. The model process maintains isothermal condition with gasification, reaction solely influenced by gasifier, knowing that in fact many reactions are exothermal, so should changes a bit. So this is the case why was so different model and experimental. And these were improvements and these things. And the effects of oxidation makes that addition helps to not up to 7 times. So 14 hydrogen per ratio hydrogen to carbon monoxide. In case of addition of catalytical, not was much too. So much higher, much less condition, less proportion, and carbon monoxide is undesired because it's toxic. So needs to be made, something made. So this is showing how it works and works how to made. The scientists didn't show why it is, especially they didn't correct this model and link. And the conclusion is as follows: at gasification, the temperature of 750, hydrogen selectivity peaked as 52%, following by decreasing trend with increasing temperature, after reaching a gasification of temperature 700. Increasing steam methane reforming enhanced selectivity of the produced but reduced uh, low very low organic structure, volatile structure. The protecting selectivity tended to stabilize at and steam methane reforming 1-1, achieving hydrogen selectivity 54, and at 800 steam methane reforming oxidation carrier methane reforming was 100 kilogram per hour of weight, yielding the reduction of 67% of waste. The economic assessment showed that production of capacity is 8 tons for 1 ton of hydrogen with profit capability of $3,000 per tons of hydrogen, operation maintenance cost at 40%, and the remuneration of investment is after 5 years. The value assessment was lowering to 30% due to compare to traditional way. So that's the all I wanted today to tell. Thank you very much for giving me voice.